Okay, picture this. You're the master architect for a brand new city. But this isn't your typical city of steel and glass. No, this one's built from silicon, and it's home to billions, literally billions, of microscopic citizens we call transistors. So what's your first job? It's to create the master blueprint. And in the world of chip design, that's exactly what we call floor planning.
So let's just think about that for a second. The scale is, well, it's pretty much unimaginable, right? How in the world do you build a city for billions of transistors? How do you make sure every single one gets the power it needs, can talk to its neighbors efficiently, and doesn't get stuck in, a massive traffic jam of data? That right there is the core challenge that floor planning is designed to solve.
And the answer, well, it all begins right here, with the chip's master blueprint. See, before we can even think about placing a single one of those billions of transistors, we have to map out the entire landscape of the chip. Getting this blueprint right, it's not just important, it's everything.
So, what exactly is floor planning? You can think of it as the big picture, strategic first step in physical design. Right now, we're not sweating the small stuff, the tiny details. We're focused on placing the big buildings, what we call macros, and laying down the essential utilities like power and water lines. That's our power grid. We're also making sure the main highways are wide enough to handle all the traffic. In our world, that's called congestion management.
Okay, so first things first. Before you can even start building, you need to know the size of your property, right? So the very first thing we have to figure out is just how big our silicon real estate needs to be. And let me tell you, this is a really careful balancing act.
And the first key metric we look at is something called core utilization. The best way to think about it is like city zoning. Basically, how much of your available land are you actually going to build on? You see, if you pack everything in super tight, say 90% utilization, yeah, you save space, but you're going to create these massive traffic jams, which we call routing congestion. But if you go too loose, well, now you're just wasting incredibly expensive silicon real estate. It's all about striking that perfect balance.
All right, next up, we have the aspect ratio. And what's that? It's actually really simple. It's just the shape of your city block, the ratio of its height to its width. Now, you might think a perfect square is ideal, right? A 1-to-1 ratio. But sometimes the final package the chip has to live in might need a more rectangular shape. And this decision is super important because it also changes how long it takes signals to get from one side of the chip to the other. That's a huge deal for timing.
And here's the really simple math that drives these big decisions. Core utilization. Well, that's just the area taken up by all your standard cells, think of those as the small residential buildings, divided by the total area of your core. An aspect ratio is even simpler, just height divided by width. These two formulas, they are the absolute foundation for figuring out our chip's dimensions.
Okay, so our city limits are set. We know the size and shape of our silicon. Now it's time to place the heavy hitters, the skyscrapers. In chip design, we call these macros. These are the big, pre-designed blocks, things like memory or entire processor cores. And where we put these, that decision pretty much dictates everything that follows. Now these aren't just, friendly suggestions, these are crucial hard and fast rules. We almost always place macros around the periphery, on the edges. Why? To keep them from blocking the flow of logic right through the middle of the chip. We also add what we call halos. Think of them as keep-out zones to give them some breathing room. And that rule about avoiding corners? That's a big one. The corners are prime real estate for the power rings that feed the entire chip. Blocking a corner is like building your skyscraper directly on top of the city's main power substation. Just a terrible idea.
So let's make this crystal clear. It's a simple do versus don't. You absolutely do want to align your macros to a nice, clean grid and give them proper spacing. What you absolutely don't want to do is just toss them in randomly, letting them overlap or block critical pathways. It's really the difference between a well-planned, functional city and just total chaos.
All right, our skyscrapers are in place. Now what? Well, now we have to power the entire city. We need to build the power grid to light everything up. And this isn't as simple as just connecting to a power source. We're talking about building a really robust infrastructure that can handle the massive energy demands of our entire Silicon City. So how do we do it? We build this grid using the thickest, highest metal layers available. Why? Because they have the lowest resistance. You can think of them as the huge, high-capacity power lines you see out in the real world. We create a mesh of power rings around the edge of the chip and then run power straps across the core. This whole setup makes sure that power gets delivered evenly to every single part of the chip, preventing any voltage drops or what you might call brownouts in our city. Okay, so before I show you the formula for this, let's be really clear about the goal. What problem are we trying to solve here?
Well, those main power rings we just talked about, they absolutely must be thick enough to handle all the current for the entire core without failing. If they're too thin, two bad things can happen. They can overheat and literally break. That's a nasty problem called electromigration, or the voltage can drop too low, which would cause the whole chip to malfunction.
And here is how we solve that problem. The formula is actually pretty straightforward. The width you need for that ring is the total current the core is going to draw, divided by the number of sides of the chip that are supplying power, times the maximum current density that specific metal can handle. It's a direct calculation that makes sure our power lines are built tough enough to handle the load.
Now, all of this theory sounds great, but how do engineers actually do this stuff in the real world? They're not drawing this out by hand with a pencil and ruler, right? No way. They use these incredibly powerful software suites called Electronic Design Automation Tools, or EDA tools, to bring this whole blueprint to life. So let's take a look at the actual commands they use.
Okay, this slide right here is pure gold for anyone who's actually working in the industry or wants to. What you're seeing are the real commands you type into the two industry-leading tools, Synopsys ICC2 on the left and Cadence Innovis on the right. And you can see they're doing the exact same things, creating the floor plan, adding power rings, adding straps, checking connectivity. They just use slightly different command names. Super practical stuff.
So you've laid out your floor plan, you've built the power grid, you're all done, right? Time to kick back? Not even close. Now comes maybe the most important part, the inspection. You have to analyze your floor plan with a fine-tooth comb to make sure it's actually going to work.
And this is basically your final inspection checklist. First, you run a congestion map. Are there any future traffic jams hiding in your design? Next, you check the utilization report. Did we use our expensive real estate efficiently? Then, and this is a huge one, you generate an IR drop map. This is what finds those brownouts we talked about. Any spot on the chip that isn't getting enough power. A bad IR drop can lead to total failure. Every single one of these checks can uncover a show-stopping flaw that you have to fix before you can move forward.
And that brings us to a final, really important question. This is the kind of thing you might actually get in a job interview. So based on everything we've just talked about, what would you do if your analysis showed a big IR drop issue? Would you make the power straps wider? Would you add more of them? Maybe change your macro placement? The right answer comes from truly understanding all these core principles of creating the chip's master blueprint.